In this video, we will discuss a problem on a three-phase induction motor. A three-phase induction motor has 460 volts rated voltage. It's a 25 horsepower, 60 Hz, 4-pole, star-connected induction motor. The equivalent circuit parameters of the induction motor are given here. This consists of the stator equivalent parameters, which are R1 and X1, rotor equivalent parameters, which are referred to the stator side, that is R2 dash and X2 dash, and Xm is given as 26.3 ohms. The total rotational losses are already given as 1100 watts and they are assumed to be constant. And these core losses are also considered to be lumped with the rotational losses. It is given that the slip is 2.2% at the rated voltage and rated frequency. Now in this problem, we need to first calculate the rotor speed, which can be calculated from the synchronous speed as well as the value of the slip given. And we need to calculate the stator current and input power to the induction motor and power factor of the input power. In order to calculate these three values, if you look at the equivalent circuit of the induction motor, the first reactance and resistance elements are corresponds to the stator equivalent circuit. Now, the current that is entering into this particular circuit is nothing but your stator current. And if you use the value of the input voltage, that is V phase and Is, then we will be getting the value of input power that is given to the induction motor. Now the power factor of this particular power, or the phase angle difference between this voltage and current, will give you the power factor of the input power. And after that, we have the problem on the rotor input power. Now, after this power given to the induction motor on the stator side, whatever the power that passes onto the rotor equivalent circuit, because these two elements are corresponds to the rotor equivalent circuit. So now, what is the amount of power that is passing this point is nothing but the power input going to the rotor. And after that power going to the rotor, the same amount of power will not be the power that is developed as the mechanical power. So we need to calculate what is the amount of mechanical power developed in the rotor, because the rotor itself will have some kind of heating losses as well as the rotational losses. In the problem, we are already having the amount of rotational losses given, but the heating losses we need to calculate from the rotor equivalent resistance itself. Based on that, we'll be able to get the amount of ultimate power that we get out of the rotor equivalent circuit. So that's what we call it as shaft output power. Then we'll be able to calculate the corresponding torque, and then we will be able to get what is the motor efficiency. Now if you try to understand how exactly is the power flow in case of an induction motor, we are already giving an amount of power to the induction motor stator, and now the stator does have some amount of losses, is what we call it as stator losses, and then the remaining amount of power after the stator losses from the input power is something that passes on to the rotor. So now you call this as power that is going to the rotor, but this is also what we call it as power that is crossing the air gap, because usually between the stator as well as the rotor there is an air gap, and the amount of power that has gone to the rotor is nothing but the amount of power that is crossing the air gap. And now once you know the amount of power that is crossing the air gap and entering into the rotor, rotor will have some kind of copper losses, and also rotor also will have some mechanical losses. So now you will have the gross mechanical power that is going into the rotor shaft, but there will be mechanical losses, and ultimately after the mechanical losses is what you will get as the shaft power output. So we need to calculate each and every stage how much is the power that we are giving in, what goes to the rotor, and what is lost in the rotor as a rotor copper losses, and what is the gross mechanical power output we are getting, and how much will be the rotational losses, and then ultimately what is the amount of torque or power that we are giving to the shaft. So this is what we will be calculating as a part of this problem. Now calculate the rotor speed. In order to calculate the rotor speed, first we need the value of the synchronous speed. So the value of the synchronous speed is usually 120 frequency of the power supply upon the number of poles. So now we have the frequency value is given as 60 Hz and we have the machine as a 4-pole machine. So if we substitute these values, then we'll be getting the speed as 1800 revolutions per minute. The same value of the synchronous speed can be given in terms of radians per second as 1800. Each revolution is 2 pi radians and every minute is 60 seconds. So if you use this, then you will have 1800 multiplied by 2 pi upon 60 radians per second as the synchronous speed. So this value we will get it as 188.5 radians per second. And next, this is what is the value of the synchronous speed. But if you wanted to get the rotor mechanical speed, so rotor speed is 1 minus s times of the synchronous speed. Now the value of the slip that is already given in the problem, that is 0.022. And if you multiply that with 1800, then you will be getting the rotor speed in terms of revolutions per minute, that is 1760 revolutions per minute. And if you want the same value of the speed in terms of radians per second, then instead of 1800 you can substitute the value of 188.5, then you will get this number as 184.4 radians per second. So the value of the rotor speed in terms of revolutions per minute is 1760, and in terms of radians per second it is 184.4 radians per second. The rotor speed is 1760 rpm or 184.4 radians per second. Now if you want to calculate the value of the stator current in the equivalent circuit, it is nothing but the current entering after the source. This is what is our stator current. In order to know the value of the stator current, you need to actually know what is the equivalent impedance of this circuit, is what we call it as Z equivalent. Now the equivalent impedance of the circuit can be calculated after you know what is the impedance on the rotor equivalent, and then combining that with the shunt reactance that we have here. If you call it as Z2 equivalent, then you can calculate that Z2 equivalent is in series with the stator equivalent resistance and reactance. Now if you want to get the value of ZR equivalent, then that is R2 dash upon the value of S plus J X2 dash. Now we know that the value of R2 dash is given as 0.332. The value of X2 dash is given as 0.464. We also know that the value of slip is 0.022. If you substitute all these numbers, then you will get the value of ZR equivalent as 15.09 plus J 0.464 ohms. Now this value of ZR equivalent is in parallel with JXM in the equivalent circuit. The resultant is what we call it as Z2 equivalent. So now if you wanted to get the value of Z2 equivalent, it is 1 upon the value of ZXM plus 1 upon the value of ZR equivalent. We know the value of XM is 26.3 ohms. And we also know the value of ZR equivalent. That's what we calculated now. If you substitute these numbers, then we'll be getting this as 1 upon 0.0773 at an angle of minus 31.1 degrees. The same thing can also be written as 12.94 at an angle of 31.1 degrees, and that's ohms because it is the value of the impedance. Now we know that this whole impedance Z2 equivalent is in series with the stator reactance and stator resistance. So if you wanted to get the value of Z total, if you wanted to get the value of Z total, so Z total is going to be Jx1 plus R1 plus the value of Z2 equivalent that we calculated. So now if you calculate that, Jx1 is J1.106 plus the value of R1 is 0.641, and we have Z equivalent as 12.94 at an angle of 31.1 degree. So now if you add all these numbers, then you will get your Z equivalent as 14.07 at an angle of 33.6 degrees, and that's ohm because it is the value of the impedance. Now as we mentioned, if you know the total value of equivalent impedance, that's what we call it as Z total, then the amount of current that is coming from your source, that is I stator, is going to be V phase upon the value of Z total that we calculated. So now we know the value of V phase because the line voltage is given as 460. Usually the V phase is going to be 460 upon root 3 because you have this induction motor being a star connected induction motor. So that's what is the phase voltage, and we have the total impedance as 14.07 at an angle of 33.6 degrees. Then you will get the value of the current as 18.88 at an angle of minus 33.6 degrees. So this is the value of the stator current for us. Once you know the value of the stator current, then you can now calculate the value of the input power, that is P input, that is given to the induction motor, and also the power factor of the input power. If you wanted to calculate the power factor of the input power, when we consider that the source is 460 upon root 3 phase voltage at an angle of 0 degrees, we know that the stator current is at an angle of minus 33.6 degrees, which is indicating that if you have your V phase, that is the stator current voltage, then your stator current is lagging at an angle of 33.6 degrees. This is what is the stator current for us. Now in that case, we can calculate the power factor of the input power as cos of 33.6 degrees, which is going to be 0.833 lagging. So the power factor, we get it there. And now if you wanted to calculate how much is the input power that is given, so that is the input power here, Pn is nothing but root 3 times of V line to line, I line, cos phi. So that's what is the input real power we are feeding into the induction motor. So now we know that the value of line voltage is 460. The value of the current that we have is 18.88, and the power factor is cos of 33.6 degrees. So if you substitute all your values of the voltage, current, as well as the phase angle difference between the voltage and current, then you will get the value of the input power as 12,530 watt. So that's the amount of power that we are feeding in to the induction motor, and the power factor is 0.833 lagging for us. We calculated the rotor speed and also the stator current, stator power, the power we are giving it to the induction motor, and also the power factor of the induction motor. So now we know that in the case of this particular induction motor, how much is the power input we are giving. So now we know the power input is 12,530 watt. Now if you wanted to calculate the rotor input power, the input power that is going to the rotor is here. So that is after you lost the losses in the stator. Now if you wanted to calculate the stator losses, that is power that is lost in the stator, that's nothing but the copper losses. So stator copper loss is going to be 3 I stator square and R1. So you have 3 phases, Now in each phase you have I square R as the losses, whereas the I here is basically nothing but the stator current, and R1 is basically stator resistance. So now I square R will give us the losses, but this is giving us the losses in phase. Now as you want to know the three-phase power losses, that is why we are having 3 times of IS square into R1. Now we calculated the value of IS, which is nothing but 18.88. So if you substitute 3 times of 18.88 square multiplied the value of R1 is 0.641. Then you'll be able to get 685 watt as the power losses that occur in the stator. Now, if you wanted to know the amount of power that has gone into the rotor, that's nothing but, we also call sometimes it as air gap power or rotor power, P rotor, or you also call it as P air gap, is nothing but P stator minus P stator copper losses. We know that the P stator is 12,530 watt and the copper losses are 685 watts. So then the leftover is 11,845 watt is nothing but the power that is going into the rotor circuit. The amount of power given as an input to the rotor circuit, or the amount of power that is crossing the air gap, which is 11,845 watt, we know that there will be rotor copper losses. So now the rotor copper losses, that is P rotor copper loss, is usually S times of P rotor. Now whatever the power that you get at the output of the rotor, which we consider it as mechanical power developed in the rotor, so that is P mechanical in the rotor, is 1 minus S times of P rotor. So now you know the value of slip, that is 2.2% or 0.022. If you substitute that 1 minus 0.022 times of the rotor power, that is 11,845, then we will be able to get the amount of power that is coming out of the rotor, or the mechanical power developed by the rotor, as 11,585 watt. So now after that, once you have this power coming out from the rotor, then there will be friction and windage losses. So the amount of power that you get at the shaft, if you wanted to know that, after this rotor power, the shaft power output is nothing but the power that we got here, that is 11,585 minus the friction and windage losses. Now it is given in the problem that these losses are 1100 watt. So now if you substitute that 11,585 minus 1100 watts, that's when we have 10,485 watt as the ultimate output that we are getting from the rotor. So that is the amount of power that we are getting as the shaft. So now we know the shaft power output. Once you know the value of the shaft power output, we can also calculate what is the induced torque and also the amount of the torque that you are getting as an output. Means the torque is induced here, but you are getting this amount of torque as an output. So this is torque induced and this is what is torque that you are getting as an output. Torque induced and torque output. Now if you want to get the torque induced is usually power induced upon the value of omega. And again, if you wanted to get the torque output, that is also the value of power output upon the value of omega. So now this omega is nothing but synchronous omega. This is what is the rotor omega for us. So now we know that the value of this is 11,585 is the amount of power induced, and the synchronous speed or omega value is 188.5 5 for us. If you substitute these two numbers, we get this as 62.8 Newton meter. Now similarly, the power output that we ultimately got is nothing but 10,485, and the value of omega for the rotor is 184.4 radians per second. So now if you substitute these two numbers, then we will get this as 56.9 Newton meter. So these are the values of the torque induced and also the total torque output that we have from the motor. And then if you wanted to know the efficiency of the motor, then the efficiency of the motor is nothing but power output upon the value of power input. So now the output power that we have is nothing but 10,485. Ultimately we got 10,485 watt as an output power for us. Whereas the input that we have, or the amount of input that we gave it to the stator, is 12,530 watt. So now if you substitute these two numbers, then you will be able to get the efficiency, and that is 83.7%. So this particular induction motor is operating with an efficiency of 83.7%.